Everything you think you know about the universe could be wrong. Scientific truths we once held as certain have been dramatically overturned, forcing us to rewrite the textbooks. This journey through 22 of the most startling reversals in cosmic thinking will completely transform your perspective on reality itself. We will uncover how the universe was once thought to be eternal and unchanging, and why astronomers were stunned to find it is not only expanding, but accelerating into the void. You will discover why we had to rethink the very nature of time and space, moving from a smooth cosmic fabric to a potentially grainy quantum foam. By the end, you will understand why questioning everything is the true engine of discovery. What current scientific fact do you suspect might be the next to fall? This concept of a universe without a beginning or end was deeply appealing, a cosmic constant in an otherwise uncertain world. The steady-state model proposed a cosmos that was essentially the same everywhere for all time. As galaxies drifted apart, new matter was theorized to spontaneously appear in the empty spaces, just enough to keep the overall density of the universe perfectly uniform forever. This idea was not some fringe theory. It was championed by brilliant minds like Fred Hoyle, who famously coined the term Big Bang during a radio broadcast, using it as a dismissive label for a theory he found deeply unattractive. The universe, in his view, was simply too elegant to have erupted from a singular, violent event. It was a grand, infinite, and self-renewing entity. Yet this elegant stability was an illusion, about to be cracked wide open by a faint, persistent noise that would rewrite cosmic history. That persistent noise was the death knell for the steady-state universe. While fiddling with a massive radio antenna in New Jersey, two astronomers named Arno Penzias and Robert Wilson were plagued by a faint, uniform hiss that came from every direction in the sky. They scrubbed the antenna of pigeon droppings and checked every component, but the hum remained, an unshakable cosmic whisper. This wasn't a faulty instrument. It was the faint, cooled remnant of the universe's fiery birth, a ghostly echo of the Big Bang itself. This cosmic microwave background radiation was precisely the evidence needed to confirm a universe that began in a state of incredible heat and density. It validated the once ridiculed idea of a primordial atom, first proposed by Georges Lemaitre. In an instant, our cosmic story was rewritten. The universe was no longer eternal and unchanging, but had a definitive, dramatic beginning. This single discovery forced a profound shift in human thought, moving us from a comfortable, infinite cosmos to one that burst into being from a single, unimaginable point. It was the first great reversal, a fundamental change in our understanding of existence that set the stage for even more startling discoveries to come. If the echo of the Big Bang rewrote our origin story, the next discovery shattered our predictions for the cosmic end. For decades, the universal consensus was clear: gravity would ultimately put the brakes on everything. After that initial explosive beginning, the collective gravitational pull of all the galaxies, stars, and dark matter was thought to be slowly but surely pulling the universe back together, perhaps destined for a final collapse. This was the elegant, intuitive model, a cosmic pendulum swinging between fire and ice. But in 1998, that pendulum broke. Two independent teams of astronomers were using distant supernova as cosmic mile markers, carefully measuring how fast the universe was expanding in the distant past. They expected to see the expansion slowing down, the telltale sign of gravity's relentless tug. What they found instead was so shocking they spent years double-checking their results, convinced they had made a mistake. The universe was not slowing down at all, it was speeding up. galaxies were flying apart from each other at an ever-increasing rate, as if some invisible, repulsive force was blowing the cosmos apart. The discovery was so utterly surprising it earned the teams a Nobel Prize. Saul Perlmutter, one of the lead researchers, described the finding as completely contrary to all expectations. This mysterious force was given a name, dark energy, and it represents a far deeper and more unsettling puzzle than dark matter. We now understand that this strange repulsive energy makes up about 70% of the entire universe. Think about that for a moment. The dominant force shaping the fate of everything we see is something we cannot see, do not understand, and never predicted. This single reversal forced a profound and humbling admission. Our models of cosmic dynamics were not just slightly off, they were missing the main character. We went from believing we understood the universe's grand trajectory to realizing we are only comprehending a tiny fraction of the forces at work. So if dark energy dictates the ultimate fate of the cosmos, what about the origins of the worlds within it? For centuries, the birth of planets was thought to be a violent and chaotic affair. The dominant theory was that our solar system came to be through a near-catastrophic event, perhaps a dramatic collision between our sun and another passing star, ripping material away to form the planets. Alternatively, planets were seen as cosmic orphans, wandering bodies that our sun's gravity simply captured as they drifted by. These were stories of cosmic chaos and sheer luck, implying that planetary systems like our own must be extraordinarily rare. The universe, in this view, was a largely empty space punctuated by lonely stars, with planets as mere accidents. This idea began to crumble in the 20th century thanks to the work of a Soviet scientist named Viktor Safronov. He proposed a theory that was far more gentle, yet infinitely more powerful. He envisioned the young sun surrounded by a vast, flat disk of gas and dust, a protoplanetary disk. Within this disk, the process was not one of violent theft, but of patient accumulation. Tiny dust grains, no larger than specks, would gently collide and stick together, gradually building up into pebbles, then rocks, then kilometer-sized planetesimals. Over millions of years, these building blocks would gravitationally attract one another, snowballing into the planets we know today. This theory of accretion painted a picture of planet formation as a peaceful, almost inevitable process, a natural outcome of a star's birth. For decades, this was a compelling but unproven model. Then, in 2014, the ALMA telescope array delivered stunning visual proof. It peered into a young star system known as HL Tauri, and the image it returned was breathtaking. There, clear as day, were concentric rings and dark gaps etched into a protoplanetary disk, the telltale signs of planets in the very act of formation, carving their orbits as they grew from the cosmic dust. This was the final, undeniable confirmation. The reversal was complete. We moved from a universe where planets were cosmic flukes born from stellar violence, to one where they are a common, gentle byproduct of starlight itself. This single shift in thinking utterly transforms our place in the cosmos, suggesting that billions of stars likely host their own families of worlds, dramatically increasing the potential for life beyond our own solar system. Even Einstein, the architect of the very equations that predicted them, refused to believe black holes could be real. He dismissed them as mere mathematical artifacts, pathological quirks in his beautiful theory of general relativity that nature would surely avoid. For decades, his view was the scientific consensus. These objects, where gravity is so intense that not even light can escape, were considered theoretical monsters, too bizarre to actually exist. They were solutions in search of a reality that did not exist. This dismissive attitude began to shift with the rise of X-ray astronomy. Scientists realized that if a black hole were in a binary system with a normal star, it could siphon material from its companion. As this stolen gas spiraled inward at tremendous speeds, it would heat up to millions of degrees, glowing not in visible light, but in high-energy X-rays. The hunt was on for such a cosmic beacon. In 1971, the breakthrough came. A powerful and flickering X-ray source was pinpointed in the constellation Cygnus, named Cygnus X1. The data was unmistakable. An invisible object far too massive to be a neutron star was relentlessly pulling matter from a blue supergiant companion. The scientific community, once so skeptical, was forced to concede. A black hole had been found. This was not just a point on a graph. It was a real, physical object devouring a star right in our own cosmic backyard. The reversal was absolute, from mathematical fiction to confirmed astrophysical reality. But the strangeness was only beginning. Stephen Hawking would later show that black holes are not the perfect, eternal prisons we once imagined. He applied quantum theory to their immense gravity and discovered they must slowly leak radiation, fading away over eons. They are not truly black but glow with a faint, theoretical heat. And in our own time, the Event Horizon Telescope collaboration has done the seemingly impossible, presenting us with a direct image of the shadow of a supermassive black hole at the heart of Galaxy M87. That now iconic fiery ring made the abstract undeniably concrete. We have stared into the abyss, and the abyss has shown us its face. The journey of the black hole is a masterclass in scientific humility, a story of how the most outlandish predictions of mathematics can, against all expectation, become the bedrock of our understanding of the cosmos. Even Einstein himself fell victim to the limits of perception, refusing to believe his own mathematics when they predicted black holes. But there was another, even more pervasive blind spot hiding in plain sight, one that would challenge our very understanding of what the universe is made of. In the 1930s, a brilliant and often cantankerous astronomer named Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies. By measuring how fast these galaxies were whirling around their common center, he made a startling calculation. The collective gravity of all the visible stars and gas was nowhere near strong enough to hold the cluster together. At the speeds they were moving, the entire system should have flown apart eons ago. Zwicky concluded there must be some form of invisible matter, which he called Dunkel Materie, providing the extra gravitational glue. His proposal was met with widespread dismissal. The idea seemed like a contrivance, an invisible fix for a problem that surely had a more conventional explanation. For decades, dark matter remained a fringe idea, an inconvenient ghost in the cosmic machine. Then, in the 1970s, an astronomer named Vera Rubin delivered the definitive proof, armed with patience and meticulous data. She focused on the rotation of individual spiral galaxies, carefully mapping how fast stars orbit around the galactic center. The expectation was simple: stars closer to the center, where most of the visible mass is concentrated, should orbit quickly. Stars out at the faint, sparse edges should move much more slowly, just as Pluto orbits the Sun far more sluggishly than Earth. But Rubin's data revealed something astonishing. The stars at the outer edges of galaxies were moving just as fast as those near the center. It was as if the entire galaxy was embedded within a giant, massive, and completely invisible halo, its gravity whipping the outer stars around at impossible speeds. This was the clincher. The evidence was no longer just in distant clusters, it was in every single galaxy she observed. The scientific community could no longer look away. The reversal was profound and humbling. We had to accept that everything we see, all the stars, galaxies, and glowing nebulae, are merely the decorative lights on the surface of a vast, deep ocean of something we cannot see. Dark matter is not a minor component, It makes up about 27% of the entire universe, outmassing all normal matter by a factor of more than 5 to 1. We went from believing the cosmos was made of what we could see to realizing we are floating in a sea of invisible giants, our vision limited to just a tiny fraction of what is truly there. Our cosmic blindness was not limited to invisible matter. It once extended to our own place in the universe. For almost 2,000 years, human beings gazed at the heavens with the absolute certainty that they stood at its very center. This was the geocentric model meticulously crafted by Aristotle and Ptolemy, a universe of perfect crystalline spheres with Earth sitting motionless at its heart. To account for the peculiar loops and retrograde motions of the planets against the starry background, the model required a complex system of circles upon circles called epicycles. It was a cosmic clockwork of breathtaking complexity, all designed to preserve one simple, comforting idea that everything in creation revolved around us. This was more than science. It was a theological and philosophical bedrock, placing humanity at the center of divine attention. Yet this elegant, human-centric universe was an illusion, a beautiful fiction about to be dismantled. The first crack appeared in 1543 with the publication of a book by a Polish cleric named Nicolaus Copernicus. On his deathbed, he unleashed a revolutionary idea. What if the sun, and not the Earth, was the center of our system? His heliocentric model was a stroke of genius, instantly simplifying the cosmos by removing many of the cumbersome epicycles, but it was not yet a complete victory. Copernicus, still bound by ancient ideas of perfect circular motion, was forced to keep a few epicycles to make his numbers work. The true death knell for the Earth-centered universe came from the tip of a telescope. When Galileo Galilei pointed his new instrument at Jupiter, he saw 4 small moons orbiting the giant planet, a clear demonstration that not everything circled the Earth. When he observed Venus, he saw it go through a full set of phases, just like our moon, something that was only possible if it was orbiting the sun. The evidence was now irrefutable. The final piece of the puzzle fell into place with Johannes Kepler, who discovered the planets do not move in perfect circles at all, but in ellipses with the sun at one focus. This single mathematical insight banished the last of the epicycles forever. The model was now not just simpler, it was profoundly more accurate. The reversal was absolute and humbling. We were ejected from the center of creation. Our world was demoted from the universe's main stage to just another rock orbiting an ordinary star. This monumental shift gave birth to the Copernican Principle, a guiding tenet of all modern science, the assumption that we hold no privileged position in the cosmos. It is a principle of profound humility, forcing us to look outward and accept that the universe was not built for us, a realization that is both terrifying and the very foundation of our quest to understand it. This demotion from the cosmic center was only the beginning of our journey toward cosmic insignificance. Even after we accepted our place orbiting the sun, we still clung to a comforting illusion about our home galaxy. For centuries, astronomers gazing at the faint Milky Band arching across the night sky assumed our solar system held a privileged spot right at the heart of it all. We believed the Milky Way was a relatively small, simple island of stars, and we were at its center. This cozy, self-important view was completely overturned in 1918 by an astronomer named Harlow Shapley. He wasn't looking at the hazy band of the Milky Way itself, but at the dense, ancient spheres of stars known as globular clusters that orbit the galactic core. By carefully measuring the distances to these clusters, he made a stunning map. He found they were not centered on our solar system at all, but on a distant point tens of thousands of light years away in the constellation Sagittarius. Our true location was not the grand central plaza, but a quiet suburb far out in the galactic Styx, roughly 26,000 light-years from the bustling core. This was another profound Copernican-style shock. A second eviction notice served from within our own cosmic home, but the revisions did not stop there. For a long time, we pictured the Milky Way as a simple, elegant spiral, like a pinwheel of stars. Then, evidence began to mount that our galaxy is not a standard spiral, but a barred spiral with a thick bar of stars cutting through its center and the spiral arms unwinding from the ends of that bar. We do not live in a perfectly symmetrical galaxy, but in one with a distinct, elongated heart, and the surprises kept coming. Data from the European Space Agency's Gaia mission, which is precisely mapping the positions and motions of billions of stars, has revealed something even more bizarre. The galactic disk, long imagined as a flat, stable platter, is in fact profoundly warped like a vinyl record left too long in the sun, its edges twisted and bent. What does this mean for us? It is a powerful lesson in perspective. Imagine trying to draw a detailed map of an entire forest while standing deep within it, unable to see the canopy or the boundaries. You are surrounded by trees, but the true shape of the woodland remains a mystery. That is our eternal challenge. Every map we make of the Milky Way is filtered through this inherent bias, our view from the inside. Each new discovery, from our suburban address to our warped galactic neighborhood, is a humbling correction. It reminds us that our most fundamental truths about our home are always provisional, always subject to revision as we learn to see with new eyes. Our understanding of the cosmos once faced a paradox so deep it threatened to unravel everything. For decades, a glaring contradiction plagued cosmology. The universe, according to the best measurements of its expansion rate, appeared to be younger than the stars it contained. Early calculations using Edwin Hubble's own data suggested a cosmos merely 2 billion years old. Yet, geologists knew with certainty that our own planet, a latecomer in cosmic terms, was at least 3 billion years old. The numbers were impossible. How could the container be younger than its contents? This was not just a small error, it was a fundamental crisis. The very timeline of existence was broken. Astronomers and physicists were forced into a difficult choice. Either our methods for dating the universe were profoundly flawed, or our understanding of how stars live and die was completely wrong. This conflict simmered for years, a nagging inconsistency that demanded resolution. The breakthrough came not from a single discovery, but from a painstaking refinement of our tools. Scientists realized that measuring the universe's expansion was far more complex than initially thought. Distances to faraway galaxies were recalibrated. Our models of stellar evolution, the intricate nuclear furnaces that power stars, were perfected. We learned that stars could burn for much longer than previously estimated. Slowly, meticulously, the gap began to close. The universe grew older as our measurements grew wiser. The culmination of this effort arrived with data from the Planck satellite, which peered into the faint afterglow of the Big Bang with exquisite precision. It gave us our current, robust age for the cosmos, 13.8 billion years. This number elegantly solved the paradox. The oldest stars we can observe, ancient balls of hydrogen and helium in the halos of galaxies, are now dated to around 13.5 billion years. The universe, at last, was comfortably older than its oldest inhabitants. This reversal from contradictory chaos to a consistent timeline is a powerful lesson. Scientific conflict is not a sign of failure, but the very engine of progress. It is the tension that forces us to look deeper, to question our assumptions, and to sharpen our methods until the pieces of the puzzle finally, beautifully, snap into place. Our own planet holds stories of ancient violence written across the night sky. The serene presence of the moon, a subject of poetry and wonder, was for centuries a deep scientific mystery. How did this massive companion come to be? Three primary theories battled for dominance, yet each fell short. The capture theory imagined the moon as a wandering rogue planet snared by Earth's gravity. This failed to explain why the moon's orbit is so perfectly stable and circular. The fission theory suggested a young, molten Earth spun so rapidly it flung a piece of itself into space, creating the Pacific Ocean basin. But the physics never added up. The energy required was simply too great. Finally, the co-accretion model argued that Earth and Moon formed side by side from the same primordial cloud of dust and gas. This was the most appealing, but it too had a fatal flaw. The Moon's composition is strangely similar to Earth's mantle, yet it is severely depleted of iron and other heavy metals. If they formed together, why are their cores so different? For decades, the origin of our closest neighbor was an unresolved puzzle, a cosmic question mark hanging over our heads. The solution, when it finally came, was more dramatic than anyone had dared to imagine. In the 1970s, a new idea began to gain traction, the giant impact hypothesis. It proposed that in the chaotic early solar system, a Mars-sized protoplanet named Theia slammed directly into the young Earth. The collision was not a gentle merging, but a cataclysmic event that vaporized part of our planet's mantle and hurled a colossal plume of molten rock and debris into orbit around Earth. From this incandescent, spinning disk of earthly material, the Moon gradually coalesced. This single, violent act explained everything: the similarity in composition between the Moon and Earth's mantle, the Moon's lack of a substantial iron core, since Theia's core would have sunk into Earth's own, and the precise angular momentum of the Earth-Moon system. Computer simulations brought this ancient catastrophe to life, showing how such an impact could naturally create our celestial partner. The clinching evidence came from the Apollo missions. When scientists analyzed the lunar rocks brought back by the astronauts, they found their isotopic signatures, their fundamental chemical fingerprints, were nearly identical to those of rocks from Earth's mantle. The Moon was not a captured stranger or a spun-off sibling. It was born from our own world's most traumatic moment. This was a stunning reversal in planetary science. We moved from a peaceful, gradual formation to a genesis of unimaginable fire and chaos. Our gentle moonlight is the enduring glow of a planetary catastrophe, a permanent reminder that creation and destruction are two sides of the same cosmic coin. That same sense of cosmic violence that forged our Moon also sculpted the distant frontier of our solar system, a realm where another long-held truth would soon face its own reckoning. For over 75 years, every child learned there were 9 planets, with tiny, distant Pluto as the plucky underdog at the very edge of our maps. Its discovery in 1930 by Clyde Tombaugh was a triumph of persistence, a new world captured on grainy photographic plates. It became an instant cultural icon, the 9th planet, a fixture in classroom models and mnemonics. This status seemed as permanent as the stars themselves, but in the 1990s, our view of the outer solar system began to shift dramatically. Powerful new telescopes revealed that Pluto was not a solitary wanderer. It was just one of countless icy bodies in a vast, donut-shaped region beyond Neptune called the Kuiper Belt. The first major crack in Pluto's planetary status appeared with the discovery of Eris, another Kuiper Belt object that initially seemed even larger than Pluto itself. If Pluto was a planet, then Eris certainly had to be one as well, and so would dozens of other similar-sized objects soon to be found. Astronomers faced a dilemma: were we about to have 50 or even 100 planets in our solar system, or did the very definition of a planet need to change? The answer came in 2006 from the International Astronomical Union. In a decision that shocked the public, they established a new, stricter definition. For a body to be a planet, it must orbit the Sun, be round due to its own gravity, and crucially, it must have cleared its orbital neighborhood of other debris. This was the rule that sealed Pluto's fate. Its orbit is crowded with other Kuiper belt objects, and it shares its celestial neighborhood rather than dominating it. Pluto was reclassified as a dwarf planet. The public outcry was immediate and emotional. It felt like a demotion, a betrayal of a childhood icon, but scientifically, this was not a demotion at all. It was a promotion of our understanding. The reversal from planet to dwarf planet was not about stripping Pluto of its importance, but about correctly placing it within a much richer and more fascinating family of icy worlds. This shift demonstrates a profound truth about science. Our categories are not set in stone. They are human-made tools that must be sharpened and sometimes completely reshaped as new evidence comes to light. The story of Pluto is a lesson in humility, reminding us that even the most cherished facts in our textbooks are provisional, always awaiting the next discovery that will force us to see our cosmic home in a new, more accurate light. The desire to find neighbors in the cosmos can be a powerful, almost irresistible force, one that famously tricked some of the sharpest eyes in astronomy. For decades, the red planet Mars was not just a world, but a canvas for our greatest hopes and fears. It all began with Italian astronomer Giovanni Schiaparelli, who in the late 19th century meticulously mapped the Martian surface and described thin, straight lines he called canali. The Italian word simply means channels or grooves, a neutral term for natural features. But when his work was translated into English, that single word became canals, a term that implies intelligent design, engineering, and purpose. This linguistic slip was a spark that ignited a global fire. The idea was seized upon and championed with fervor by the wealthy American astronomer Percival Lowell. He built a prestigious observatory in Flagstaff, Arizona, dedicated largely to studying Mars, and he saw the canals everywhere. In his detailed drawings, the planet was crisscrossed by a vast geometric network of straight lines, a global irrigation system built by a desperate, dying civilization to channel water from the polar ice caps to their arid cities. Lowell's vision was compelling and complete, a narrative of intelligent Martians that captured the public imagination and dominated popular culture for a generation. But were these canals real? Other skilled observers using similar telescopes strained to see them and saw nothing but a blurry, patchy surface. The lines seemed to appear and disappear, their positions shifting. The scientific community was divided, a schism between what some believed they were seeing and what others simply could not confirm. The truth, when it finally arrived, was a lesson in the fallibility of human perception. The canals were a perfect storm of optical illusion. Astronomers were pushing their telescopes to the absolute limit of resolution, staring for hours at a tiny, shimmering disk seen through the turbulent ocean of Earth's atmosphere. In those moments of extreme visual strain, the human brain, which is hardwired to find patterns and connect dots, would unconsciously link together faint, unrelated patches and dark splotches on the Martian surface, creating the illusion of straight, artificial lines. There was no grand architecture, no dying civilization. The final, definitive blow came not from a better telescope on Earth, but from our first robotic emissaries. The Mariner 4 spacecraft flew past Mars in 1965, and its crude camera captured a world that was shockingly lunar, pockmarked with craters and seemingly dead. Then the Mariner 9 orbiter in 1971 mapped the entire planet, revealing a world of breathtaking natural wonder with colossal volcanoes, a canyon system that dwarfs the Grand Canyon, and ancient riverbeds, but not a single canal. The Viking landers that followed sent back postcards from a barren, rust-colored desert, utterly devoid of any structure built by intelligent hands. The great Martian canal civilization vanished, not from the planet but from our minds. This episode stands as one of the most cautionary tales in science, a stark reminder of how easily our expectations can shape our observations, how we can sometimes see what we wish to see rather than what is actually there. It underscores the absolute necessity of technological verification, of sending machines to see with cold, impartial eyes what our own hopeful gaze could not. Our search for cosmic neighbors often reveals more about our own limited perspective than about the universe itself. This pattern of underestimation is perfectly captured by the ever-shifting boundary of our own solar system. For generations, we believed we had mapped its full extent, only to be proven wrong time and again. The ancients knew of planets out to Saturn, the ringed wonder that seemed a fitting final sentinel. Then, in 1781, William Herschel's telescope revealed Uranus, a new world that instantly doubled the known size of our cosmic backyard. Neptune followed in 1846, discovered not by chance but through mathematical prediction, its gravity subtly tugging at Uranus' orbit. Each discovery was a shock, pushing the frontier billions of miles farther into the darkness. With Pluto's discovery in 1930, we felt certain we had at last found the final planet, the ultimate edge. Yet this was still an illusion, a failure to grasp the true scale of our sun's dominion. The real turning point came in 1992, when astronomers David Jewett and Jane Liu confirmed the existence of the first Kuiper belt object since Pluto. It was a small, icy body orbiting in the cold vastness beyond Neptune. This was not just another planet, it was a glimpse of an entirely new realm. Suddenly, Pluto was not a solitary outpost, but the king of a vast, populous belt of icy worlds. Our solar system had grown once more, not by adding a single point of light, but by revealing an entire hidden continent at its frontier. But where does it truly end? The answer came from our most distant robotic envoys. The Voyager 1 and 2 probes, after touring the giant planets, kept speeding outward. They eventually crossed a turbulent boundary known as the heliopause, the region where the sun's constant stream of particles, the solar wind, is finally halted by the pressure of the interstellar medium. This is the true shoreline of the sun's influence, yet even this is not the final border. We now understand that our system is enveloped by the Oort cloud, a theoretical sphere of icy planetesimals so distant that the sun is just a bright star in their sky. This cloud is the source of long-period comets, and its outer edge is staggeringly remote, perhaps a light year from the sun, a quarter of the way to our nearest stellar neighbor. This continuous expansion of our home system's map is a profound lesson in cosmic humility. Each generation looks at the edge of the known and assumes they are seeing the final frontier, only for the next to reveal that the frontier was merely a signpost for a much vaster territory beyond. We are forever drawing maps of a coastline that never ends. Einstein's unwavering cosmic speed limit, the constancy of light's velocity, has long been a cornerstone of modern physics. It is the absolute rule woven into the fabric of space-time itself, a number so fundamental that our entire understanding of the cosmos depends on it remaining unchanged since the first moment of time. Yet a small but serious group of physicists has begun to ask a heretical question. What if this most sacred of constants is not so constant after all? What if the speed of light was different in the violent infancy of the universe? This is not a question asked lightly. It strikes at the very heart of relativity. The proposal, known as varying speed of light cosmology, suggests that in the first fleeting instants after the Big Bang, light traveled at a rate exponentially faster than it does today. Why would anyone entertain such a radical idea? Because it offers an elegantly simple solution to two of cosmology's most stubborn puzzles. The horizon problem asks why the universe looks so uniform in every direction. Distant regions on opposite sides of the sky have the same temperature and density, but in a universe with a fixed light speed, there simply hasn't been enough time since the beginning for light or heat to travel between them and even things out. They were never in contact. How can they be so perfectly matched? Then there is the flatness problem. Our universe appears incredibly finely tuned, its expansion rate and density balanced on a knife's edge. A tiny deviation either way in the early universe would have led to immediate collapse or a catastrophic, frigid rip. The odds of such perfect balance seem astronomically low. A faster speed of light in the primordial cosmos elegantly resolves both issues. If light could travel much faster back then, it could have crisscrossed the entire universe in an instant, creating the uniformity we see. That immense speed would also have ironed out any curvature in spacetime, forcing the universe into the flat geometry we observe. It is a single, powerful tweak that smooths out two major wrinkles in our standard model. The evidence for this staggering idea is tentative but tantalizing. Some studies of light from distant quasars, which has been traveling for billions of years, have hinted at tiny variations in a related fundamental constant, the fine structure constant. If that constant has changed, it implies the speed of light may have as well. Other researchers have looked for signatures of this variation etched into the cosmic microwave background, the fossilized light from the Big Bang. The results are not yet conclusive, and the majority of physicists remain deeply skeptical, as they should be. The constancy of light speed is not a principle we abandon without overwhelming proof. But the mere fact that this idea is being seriously debated in respected journals represents a profound shift in scientific thinking. We are no longer just asking what the laws of nature are. We are daring to ask if they themselves have a history, if the very rules of the game were written differently in the deep past. To question the speed of light is to question the stability of reality's foundation. An act of intellectual bravery that ensures physics remains a living, breathing, and endlessly self-critical pursuit. This same questioning of fundamental constants leads us to an even more radical possibility, one that redefines the very meaning of reality. The concept of a multiverse has journeyed from the fringes of philosophy to the forefront of cosmological debate. For most of scientific history, the idea that our universe is just one bubble in a frothing cosmic sea of universes was dismissed as pure metaphysics, untestable and therefore outside the realm of science. How could we ever prove or disprove something that exists beyond the ultimate horizon of our own spacetime? Yet, the idea refused to fade because it emerged naturally from our most sophisticated theories. The dominant model of cosmic inflation, which describes the universe's exponential expansion in its first moments, suggests that this inflationary process may not be a one-time event. Instead, it could be eternal, with new pocket universes continuously bubbling into existence, each with its own unique set of physical laws and constants. String theory, an attempt to unify all forces of nature, mathematically allows for a staggering number of possible vacuum states, perhaps 10 to the power of 500, each representing a different kind of universe with different particles and forces. Our universe, with its seemingly fine-tuned constants that allow for stars, planets, and life, might not be a miraculous accident. but simply a lucky draw from an infinite cosmic lottery. Physicists like Max Tegmark have created detailed classifications of multiverses, from the simple level 1 multiverse, where our observable universe is just one patch in a much larger, infinite space, to the truly bizarre level 4, where entirely different mathematical structures govern separate realities. This represents a staggering reversal in scientific thinking. We have shifted from assuming our universe is a unique, special entity to seriously considering that it might be utterly ordinary, one page in an infinite library of realities. While the multiverse remains fiercely controversial and may forever be beyond direct observation, its growing acceptance as a plausible, if unproven, concept marks a profound expansion of human imagination. It challenges us to ask, what is reality if our entire cosmos is just a single experiment running in a much grander laboratory? Isaac Newton envisioned time as a perfect, universal river, flowing at the same steady rate for everyone and everything, from a falling apple to a distant star. This absolute time was the unwavering drumbeat of the cosmos, a background stage upon which all events played out. It was an intuitive, comforting idea, one that matched our everyday experience. But this bedrock certainty was shattered by Albert Einstein. His theory of relativity revealed that time is not a single, universal stream. It is a fluid, personal experience, warped by gravity and stretched by motion. A clock on a satellite in orbit, for instance, ticks measurably faster than one on the Earth's surface, a crucial correction needed for the GPS in your phone to function accurately. An astronaut traveling at near light speed would return to Earth to find that less time has passed for them than for the people they left behind. Time, in essence, is not a backdrop. It is a participant, woven together with space into a single, malleable fabric. Yet this revolutionary picture is now facing an even more profound challenge from the quantum realm. In the world of the very small, time seems to behave differently. Quantum mechanics suggests that at the most fundamental level, time might not be smooth and continuous, but granular, composed of discrete, indivisible moments, much like a movie is made of individual frames. This creates a direct conflict with relativity's flowing spacetime. How can a smooth fabric also be made of tiny, separate grains? This has led some physicists like Carlo Rovelli to propose a truly staggering idea, that time does not exist at all at the most fundamental level of reality. In this view, what we perceive as the flow of time is an emergent illusion, a consequence of the complex interactions of countless quantum events. It is a cosmic magic trick where change itself creates the mirage of temporal passage. The very order of events, the feeling of past, present, and future, may be nothing more than a story our brains tell us to make sense of a timeless, interconnected web of relationships. This evolving understanding forces us to confront a humbling possibility that our most intimate experience, the relentless forward march of time, may be the greatest illusion of all. The elegant simplicity of the Big Bang theory hid deep, unresolved flaws. It beautifully described an expanding universe, but it could not explain why the cosmos looked so perfectly uniform in every direction. Distant regions of space, billions of light-years apart, had the same temperature and density, yet according to the standard model, these regions had never been in contact. There simply hadn't been enough time for light or heat to travel between them and even things out. This was the horizon problem. Then there was the flatness problem. The geometry of our universe appears incredibly flat, a perfect balance between expansion and gravitational pull. The odds of such a precise, knife-edge balance from a random beginning seemed astronomically low, like balancing a pencil on its tip for billions of years. The universe we observed was too uniform and too flat for the classic Big Bang story to be the whole story. In 1980, a young physicist named Alan Guth was working on a different problem altogether, concerning the behavior of grand unified theories in the early universe. His calculations kept pointing toward a startling possibility. He realized that a peculiar type of energy field, a false vacuum, could generate a repulsive gravitational force of unimaginable power. If such a field existed in the first fraction of a second after creation, it would have caused the universe to expand not just rapidly but exponentially. Guth called this process inflation. For a fleeting moment, far less than a blink of an eye, the fabric of space itself would have ballooned at a speed far greater than light, doubling in size every tiny fraction of a second. This wasn't expansion within space, it was the explosive stretching of spacetime. This single, brilliant insight solved both major problems at once. Inflation took a tiny, subatomic patch of the early universe that had already achieved a uniform temperature and stretched it to become larger than our entire observable cosmos, creating the large-scale uniformity we see today. At the same time, this phenomenal stretching would have ironed out any primordial wrinkles or curvature, forcing the universe into the flat geometry we measure, just as blowing up a balloon makes its surface appear flatter and flatter. The theory made a crucial prediction. The quantum jitters from that inflationary field would have been stretched across the universe, creating minute ripples in density that would later serve as the gravitational seeds for all cosmic structure, every galaxy and cluster we see today. These ripples should be faintly imprinted on the oldest light in the universe, the cosmic microwave background. For years, this was a theoretical dream. Then, in the early 1990s, the COBE satellite mission looked at the cosmic background with unprecedented precision and found exactly that, the telltale fingerprints of those primordial density variations. It was a stunning confirmation, yet the story of inflation is not one of a single, finished idea. It is a living theory that has itself evolved dramatically. The simplest models proposed by Guth had their own issues, leading to new versions like chaotic inflation and eternal inflation, the latter suggesting our entire cosmos is just one bubble in an endlessly inflating multiverse. And today, as our observations of the cosmic microwave background grow ever more precise, some of the simplest inflationary models are facing tension with the data. The predicted patterns of gravitational waves from inflation have not been found at the levels some versions of the theory expected. This has led some physicists to question the entire paradigm, while others are developing more complex and nuanced models to fit the new evidence. The journey of cosmic inflation is a masterclass in how science truly works. It represents a shift from a single, simple explosive event to a layered, complex early universe history. It shows that a theory is not a final answer, but a framework that must adapt, evolve, and sometimes be completely reimagined to overcome the limitations of its predecessors, constantly refining our picture of reality against the hard stone of observational data. That same reliance on elegant mathematics over physical intuition would solve another deep crisis, one involving a ghost that haunted physics for centuries. The idea was simple and felt undeniably true. If light is a wave like sound or water, then it must be waving in something. Sound needs air, water needs the ocean, so light, scientists reasoned, must need a medium to ripple through. They called this invisible, all-pervading substance the luminiferous ether. It was imagined as a static, frictionless sea filling the void of space, the absolute frame of reference against which all motion could be measured. The entire universe was thought to be swimming through this mysterious, undetectable fluid. Proving its existence became one of the great quests of 19th-century physics. In 1887, two American scientists, Albert Michelson and Edward Morley, designed an exquisitely sensitive experiment to finally catch the ether wind. Their device, an interferometer, split a beam of light and sent the two parts racing on perpendicular paths before recombining them. The logic was flawless. As Earth plowed through the stationary ether on its orbit around the Sun, the light beam traveling with the ether's current should have a slightly different speed than the beam traveling across it, just as a swimmer moves faster going downstream than crossing the river. This speed difference would cause a tiny shift in the light waves when they reunited, a telltale interference fringe. Michelson and Morley prepared to measure this shift, confident they were about to confirm one of physics' bedrock assumptions. The result was a shock. They found nothing, no shift, no fringe, no hint of an ether wind at all. It was as if the swimmer found the river did not exist, and they were swimming in a stationary pool no matter which direction they looked. The experiment was repeated at different times of the year with ever greater precision, but the answer was always the same. There was no ether to be found. This null result was a catastrophe. It created a profound paradox that threatened to unravel classical physics. How could light be a wave with nothing to wave in? For nearly 20 years, physicists struggled, proposing increasingly convoluted ideas to save the ether concept, even suggesting that objects physically contracted in the direction of their motion through the ether to hide the effect. These fixes were ugly and unsatisfying. The solution required a radical new perspective, one that would come from a young patent clerk named Albert Einstein. In 1905, his theory of special relativity resolved the crisis with breathtaking simplicity. He started from two principles: that the laws of physics are the same for all observers moving at constant speed, and that the speed of light in a vacuum is always constant, no matter how fast the source or the observer is moving. From these postulates, a new reality emerged. There was no need for an ether because there was no absolute state of rest. Space itself was the arena, and it was not a substance but a void. The speed of light was not constant relative to a mysterious medium. It was a fundamental constant of the universe, a universal speed limit. This was a staggering conceptual reversal. We abandoned a tangible, material medium for a reality where space and time are relative and intertwined. The mathematics of relativity was far more elegant and powerful than the clunky ether model it replaced. The death of the ether stands as a timeless lesson in scientific progress. It shows us that sometimes the most elegant solution is not to find an answer, but to realize that the entire question was built on a foundation of sand. By letting go of a deeply held common-sense assumption, we cleared the way for a far more profound and accurate understanding of the cosmos. The ultimate destiny of everything was once thought to be a simple choice between fire and ice. Would the universe fall back in on itself in a fiery big crunch, or would it expand forever into a cold, dark, and silent emptiness? For most of the 20th century, cosmologists debated these two starkly different endings. The discovery of dark energy and the accelerating expansion in 1998 seemed to deliver a final, chilling verdict. The universe would not collapse. Instead, it would fly apart for all eternity, heading toward a state known as the Big Freeze or heat death. This is not a dramatic explosion, but the quietest ending imaginable. Over trillions upon trillions of years, stars will burn out, galaxies will evaporate, and black holes will slowly evaporate through Hawking radiation. All temperature differences will even out until the entire cosmos reaches a uniform, frigid temperature, just a fraction of a degree above absolute zero. In this final state, no energy can flow, no work can be done, and no life or complex process of any kind is possible. It is the ultimate, irreversible thermodynamic equilibrium, a cosmic graveyard where time itself may cease to have meaning. This seemed to be the last word, a bleak but scientifically robust conclusion. Yet the story of our cosmic fate is far from over. The very force that sealed this destiny, dark energy, is now the source of new and even more dramatic possibilities. What if dark energy is not constant? Some theoretical models suggest it could grow stronger over time, its repulsive force becoming more and more dominant. In this scenario, we would not face a slow freeze, but a violent and instantaneous end known as the Big Rip. Imagine the repulsive force of dark energy growing without bound, eventually overwhelming every force that holds the universe together. First, galaxy clusters would be torn asunder, then individual galaxies. As the force intensifies, stars would be ripped from their planetary systems. In the final moments, planets, then atoms, and even the very fabric of spacetime itself would be shredded into nothingness. The universe would end not with a whimper, but with a catastrophic tear in the continuum of reality. Is this our future? We simply do not know. The true nature of dark energy remains the single greatest mystery in cosmology. Our understanding of the universe's final chapter is not a closed book, but a manuscript constantly being revised with every new observation from our most powerful telescopes. The ultimate fate of all we see hangs in the balance, a profound reminder that even our grandest cosmic predictions are still written in pencil, awaiting the next discovery that might force us to erase them and start again. For centuries, the star was the ultimate unit of the cosmos. These brilliant points of light were the fundamental building blocks, scattered across what we believed was a single, all-encompassing galaxy. Even the hazy smudges we called nebulae were thought to be mere clouds of gas within our own Milky Way, minor features in a stellar-dominated universe. This entire perspective shattered in the 1920s, when Edwin Hubble trained the powerful Hooker telescope on the Great Nebula in Andromeda. He identified a special kind of star, a Cepheid variable within its glow. By measuring its pulse, he could calculate its true distance, and the result was staggering. Andromeda was not a nearby cloud. It was an island universe in its own right, a colossal city of stars millions of light years beyond our own. In a single observation, the cosmos exploded in size. Galaxies were now the new fundamental units, the primary structures of the universe. But this was only the first layer of a much larger, more complex architecture. As our maps improved, we saw that galaxies were not scattered randomly. They gathered in clusters bound together by gravity, and these clusters themselves formed into sprawling superclusters. Our own Milky Way is part of a small group, which in turn lies on the outskirts of the vast Virgo cluster. Yet even this seemed insufficient to describe the grand design. With the advent of massive digital sky surveys, a breathtaking pattern emerged, a cosmic web. We now see that the universe is structured around immense filaments of dark matter and galaxies, stretching for hundreds of millions of light years like the strands of a spiderweb. These filaments surround vast, empty voids, regions of startling nothingness that can span hundreds of millions of light years across. Our entire local universe, including the Virgo cluster, is now understood to be a single tendril within an even greater structure known as the Laniakea supercluster, a gravitational watershed containing over 100,000 galaxies. Each time we thought we had found the largest possible structure, a new, grander level of organization revealed itself. This expanding hierarchy forces a profound shift in perspective. We are not just living in a galaxy, we are residing within a specific neighborhood of a continent that is itself part of a cosmic supercontinent, all woven into a web of unimaginable scale. The universe is not a simple collection of stars or even galaxies. It is a dynamic, interconnected architecture where the true building blocks are these immense patterns in the fabric of space itself. The hunt for a hidden giant began not with a telescope's gaze, but with the strange choreography of distant ice. After Pluto was reclassified, our outer solar system seemed fully mapped, a collection of small, frozen worlds orbiting in predictable paths. Yet, as astronomers discovered more of these distant objects in the Kuiper belt, a bizarre pattern emerged. Their elongated orbits were not just random, they were clustered together, all pointing in roughly the same direction and tilting in the same way, like a school of fish moving against a current. The odds of this happening by pure chance are astronomically low. In 2016, astronomers Konstantin Batygin and Mike Brown ran the numbers and proposed a stunning explanation: a massive, unseen planet, perhaps 10 times the mass of Earth, lurking in the profound darkness far beyond Pluto. This hypothetical world, temporarily dubbed Planet 9, would be so distant that a single orbit around the Sun could take up to 20,000 years. Its immense gravity, they argued, is the invisible hand herding these smaller objects into their peculiar, aligned orbits. This represents a profound reversal in our thinking, a shift from the confidence that we had catalogued all the major players in our solar system to the thrilling suspicion that a true giant remains hidden in the shadows, so far away that it reflects virtually no sunlight for our telescopes to catch. The search for Planet 9 has since become one of astronomy's great modern quests, with teams around the world scanning the skies with some of the most powerful observatories available. They are looking for a single, faint pixel of light moving slowly against the backdrop of fixed stars. It is a needle in a cosmic haystack of unimaginable scale. Yet, the very fact that we are looking at all is a testament to the power of prediction. We are not just staring into the void hoping to see something. We are being guided by the subtle whispers of gravity, by the way small objects dance to the tune of a maestro we have not yet seen. Whether Planet 9 is ultimately found or if another explanation for the orbital clustering emerges, its prediction has already changed our perspective. It challenges the comforting assumption that we have fully explored our own cosmic backyard, reminding us that our solar system is a dynamic and still mysterious place, capable of hiding worlds of staggering size just beyond the edge of our current vision. Einstein's smooth cosmic fabric may be an illusion. The elegant continuum of spacetime, so central to general relativity, could dissolve into a seething, chaotic foam at the very smallest scales. This is the quantum realm, where the rules of gravity and particle physics collide in a profound conflict. On one hand, relativity paints a picture of space and time as a unified, flexible sheet, warped by mass and energy. On the other, quantum mechanics insists that everything, including energy, comes in tiny, indivisible packets. So why should spacetime itself be any different? This suggests that if you could peer down to the Planck scale, a distance a billion trillion times smaller than an atom, you would not see a smooth surface. You would find a turbulent, probabilistic froth where tiny virtual particles and wormholes blink in and out of existence. It is a reality where the concepts of here and there, before and after, lose all meaning. This radical idea has spawned two leading but competing theories for a quantum theory of gravity. Loop quantum gravity proposes that space itself is woven from a network of finite, interconnected loops, a spin network where area and volume are quantized. String theory, in contrast, suggests that the fundamental entities are not points, but tiny, vibrating strings, and that spacetime emerges from the complex interactions of these strings within extra dimensions. Both are attempts to stitch the smooth fabric of relativity to the granular world of the quantum, but they approach the problem from opposite directions. The quest for proof is as audacious as the theories themselves. Scientists have turned the universe into a laboratory, using the most energetic events imaginable. When a distant gamma ray burst erupts, it sends photons of different energies racing across the cosmos for billions of years. If space-time is truly grainy, the theory goes, the higher energy photons should interact with this quantum foam ever so slightly, causing a tiny delay compared to their lower energy counterparts. It would be like two runners on a sandy beach, where the heavier runner sinks in just a bit more with each step. Experiments have searched for this telltale lag, but so far, the results remain elusive. The smooth fabric of Einstein's universe has yet to reveal its hidden grain. This potential reversal from a continuous to a discrete reality is not just a technicality, it is a revolution waiting to happen. It would mean that the stage upon which the cosmic drama plays out is not fundamental, but itself emerges from something deeper and more strange. Resolving this tension may require us to abandon our most cherished intuitions about the nature of reality itself, pointing toward a new physics we have only begun to dream of. For centuries, the sheer suitability of our universe for life was dismissed as a happy accident, a cosmic coincidence with no deeper meaning. The perfect balance of physical constants, the precise strength of gravity, the exact mass of the electron, all seemed like an incredible stroke of luck. To suggest there was any purpose or design behind it was considered unscientific, a throwback to an older, teleological way of thinking. Science demanded a universe indifferent to its inhabitants, a random collection of particles where we were just a fortunate bit of flotsam. But as our measurements grew sharper, the coincidences became too staggering to ignore. The universe does not merely permit life, it seems exquisitely fine-tuned for it. If the force that binds atomic nuclei were just a few % stronger, the universe would be all helium, with no hydrogen to fuel stars or form water. If it were slightly weaker, complex atoms could never form at all. If the cosmological constant, which drives the acceleration of the universe, were a little stronger, galaxies would never have coalesced. A little weaker, and everything would have collapsed back in on itself long ago. The list of these razor-edge balances goes on and on, creating a picture of a cosmos that feels suspiciously hospitable. This mounting evidence forced a profound philosophical shift, giving new credibility to what is known as the Anthropic Principle. In its simplest form, it states that we should not be surprised to find the universe fine-tuned for life, because if it were not, we would not be here to observe it. Our existence acts as a selection effect on our observations. It is not that the universe was made for us, but that we are a product of a universe capable of making us. This is not an explanation in itself, but a framework for asking the right questions. The most powerful application of this principle comes from its integration with the multiverse concept. If an infinite or near-infinite number of universes exist, each with its own random set of physical constants, then it is no longer surprising that we find ourselves in one of the rare, life-permitting bubbles. In this vast cosmic landscape, most universes would be stillborn or barren, but a precious few would, by sheer statistical chance, have the right recipe for stars, planets, and observers. We do not live in a special universe, we live in a viable one. This remains one of the most controversial ideas in modern science, with critics arguing it is an untestable retreat from fundamental explanation. Yet its influence is undeniable. It represents a complete reversal from dismissing life's conditions as mere accident to seriously considering how our own presence biases our view of reality. The Anthropic Principle is a humbling reminder that we are not passive witnesses to the cosmos. We are active participants whose very existence filters what we are able to see, forcing us to question whether the universe we perceive is the only one possible, or simply the only one we can ever know. These 22 startling reversals are not just isolated errors, but chapters in a much larger story about how knowledge itself evolves. When we step back, clear patterns emerge from this cosmic dance of discovery and correction. The process is rarely one of a simple fact being replaced by another. More often, it follows a cycle described by the philosopher Thomas Kuhn as a paradigm shift. For long periods, what he called normal science operates comfortably within an accepted framework, solving puzzles and filling in details. But over time, anomalies accumulate, observations that stubbornly refuse to fit the established model. At first, these are dismissed as errors or ignored, but when the contradictions become too numerous and too profound, the entire framework can no longer hold. This triggers a scientific revolution, a dramatic overturning of the old worldview in favor of a new one that can explain the anomalies. The shift from an Earth-centered universe to a heliocentric one was a classic paradigm shift, as was the move from a steady-state cosmos to the Big Bang. In each case, the old model didn't just get a few details wrong, it was fundamentally the wrong way of seeing reality. Another powerful theme woven through these stories is the relentless erosion of our cosmic specialness. Time and again, we have been moved from the center to the periphery, from a universe built for us to one that is largely indifferent. Our planet is not the center of the solar system. Our sun is not the center of the galaxy, and our galaxy holds no privileged place in the universe. This trend toward what we call the Copernican Principle is a humbling but necessary correction to our ego. It forces us to see the universe as it is, not as we wish it to be. What is the common thread enabling these breakthroughs? It is almost always a new way of seeing. The telescope shattered the crystalline spheres of the ancient cosmos. Radio telescopes detected the faint whisper of the Big Bang. Space-based observatories measured the accelerating expansion driven by dark energy. Computers allowed us to simulate the violent birth of the moon or map the invisible filaments of the cosmic web. Our conceptual revolutions are almost always preceded by a technological one, granting us new senses to perceive the universe. This long history of overturned certainties offers a crucial lesson for today. The most dangerous phrase in science is "we know." The established truths of any era are merely the best explanations we have with the evidence available at the time. They are always provisional, always subject to revision. The great physicist Max Planck noted that science advances one funeral at a time, a grim but often accurate observation about how deeply we cling to our paradigms. So, as you look at the night sky, remember that some of the facts you hold as certain will one day be seen as historical curiosities. This is not a weakness of science, but its greatest strength, its endless capacity for self-correction. The true constant in our exploration of the cosmos is not any particular fact, but the inevitability of change itself. This long parade of overturned truths reveals a pattern far deeper than a simple list of errors. Scientific progress is not a steady march toward a final answer, but a chaotic and unpredictable dance of correction and refinement. Each of these 22 startling reversals did more than just swap one fact for another. They fundamentally expanded what we thought was possible, while simultaneously humbling our ancient desire to be the center of everything. We were moved from the cosmic main stage to a speck orbiting an ordinary star in a warped galaxy, adrift in a sea of invisible matter and pushed apart by a mysterious dark energy. The universe we inhabit today is infinitely stranger, more vast, and more wonderful than the one we thought we knew a century ago. The true value of this journey is not found in the fallen theories themselves, but in the powerful process they represent. Science at its heart is not a collection of facts, but a method of relentless questioning. It is a system built on the courage to say we were wrong, and the humility to accept that our current best explanation is almost certainly incomplete. This self-correcting mechanism is what allows our understanding to evolve, to shed its skin and grow. As we build ever more powerful telescopes and probe deeper into the quantum realm, we must not only expect more startling reversals, we should welcome them. They are the sign that we are pushing against the boundaries of the known, and that our journey of discovery is far from over. The greatest scientific discovery may ultimately be this, the profound realization that the more we learn, the more we understand how much remains a magnificent and thrilling mystery. If these cosmic paradigm shifts have captivated your imagination, you can continue this journey with us. Subscribing to the channel ensures you never miss our next deep dive into the mysteries of space, where we constantly explore the ideas that challenge conventional thinking. We would love to hear your thoughts in the comments below. Tell us which of these 22 reversals surprised you the most, or make your own prediction. Which current scientific fact, the one we all take for granted today, do you suspect will be the next to fall? Your participation and engagement are what make this community so vibrant, and they directly support our mission to make these profound cosmic concepts accessible and thrilling for everyone. If you enjoyed this voyage through science's greatest upheavals, please give this video a like. It truly helps others discover this content. For those eager to delve even deeper, be sure to check the description for a curated list of books, articles, and documentaries on these fascinating topics. Thank you for watching, and until our next exploration, keep looking up at the stars and never stop questioning everything you think you know. That relentless curiosity, after all, is where the next great scientific revolution always begins.